Hello मेरे प्यारे बच्चों. Welcome back to another quick revision session. I know exams are near, so tension नहीं लेने का. We are going to make this chapter super simple for you. चलो बच्चों, let's quickly see the 5 simple steps we will take to become masters of this chapter. It's going to be easy, I promise.
First up, let's figure out why we even need semiconductors in the first place. You know, it all started with a really big problem in old electronics.
Just look at the difference here. I mean, the old vacuum tubes, they were bulky, they ate up so much power, and honestly, not very reliable. But then, look at our modern semiconductor devices. They're small, super efficient, and they last for a really long time. Can you imagine? Your mobile phone would be the size of a whole room if we were still using those old tubes.
So, what is the secret? The secret code that makes some materials conductors and others insulators? Well, the answer is in something called energy bands. Let's dive right into this and crack the code.
Okay, just think of it like an apartment building for electrons. The valence band, that's their home floor. That's where they live. And the conduction band, well, that's the playground floor where they can just run around freely and conduct electricity. Simple, right?
So in metals, it's really cool. The home floor and the playground floor are basically connected. They overlap, so the electrons can move freely, which is exactly why metals conduct electricity so well. No problem at all. Now in insulators, it's the total opposite. The playground is on a very high floor, and guess what? There's no lift. This gap is huge. The electrons are just stuck at home and they cannot conduct electricity. It's impossible for them. And this is where things get really interesting, butcho. Semiconductors. For them, the gap is small. It's manageable. So with just a little bit of energy, maybe some heat, a few electrons can make that jump to the playground. And this is what makes them so special.
So here we see a pure semiconductor, what we call intrinsic. And honestly, at low temperatures, it's a little bit boring. All the electrons are just perfectly bonded, holding hands with their neighbors.
But you know what? A pure semiconductor isn't very useful. The real magic happens when we add a special ingredient. And this process, it's called doping. It's just like adding a special masala to a dish to give it that amazing flavor. Yep. Doping gives the semiconductor its superpower. This is how we can control it. So here's the crucial point, Bacha. If you add an impurity with 5 electrons, you get extra electrons. We call this N-type. And for negative, simple. And if you add an impurity with only 3 electrons, you create a vacancy, or what we call a hole, and this becomes a P-type semiconductor. P for positive.
Okay, Butcho, pay attention. This is a very common exam question. Let's see the answer and get those easy marks.
See? It's so simple. In N-type, N is for negative, so electrons are the majority. Easy peasy.
Okay, so what happens when we bring an N-type and a P-type semiconductor together? This amazing team-up creates the P-N junction, and believe me, this is the heart of all modern electronics. The moment they meet, electrons from the N side just rush to fill the holes on the P side. This creates a barrier in the middle called the depletion region. Just think of it like a very strict security guard at a gate who won't let anyone pass. But what if we connect a battery? If we connect the positive terminal to the P side and negative to the N side, this is called forward bias. We basically push everyone towards the gate. The barrier becomes small and bam! Current flows easily. The gate is open. Now, if we connect it the opposite way, what we call reverse bias, we pull everyone away from the gate. The barrier becomes huge, and the current just stops. So you see, this is the diode's main trick. It's a one-way street for current. Okay, so we have this amazing one-way gate for current. So what is its most important job in all our devices? Let's find out.
You know how our wall sockets give us AC, right? But our phones and laptops, they need DC. So the device that does this super important conversion is called a rectifier. And who's the hero inside? Our PN junction diode.
So the simplest rectifier just uses one diode. It lets the positive half of the AC wave pass, but it completely blocks the negative half. It's a bit inefficient, right? We're wasting half the power. But the full wave rectifier, now this is much smarter. It cleverly uses diodes to flip the negative half of the wave and make it positive too. See? Now we get a continuous DC current. And this, Bacho, is the secret inside all our chargers.
So Bacho, if you just remember these key points, you are all set for your exam. This is the summary of the whole chapter. Take a screenshot if you want. Semiconductors have a small energy gap. We increase conductivity with doping. The p-n junction is a one-way diode. Forward bias is on, reverse bias is off, and its main job is to convert AC to DC. Got it?
And that was it. Simple, right? So just think about this. How does this one simple property, allowing current to flow in only one direction, how does that power the entire digital world we live in? It's amazing. Revise these points, Bacho, and you will do great. Until next time, keep learning and don't take any stress. All the best.